Now we have a charged ring that has a radius of 2 centimeters, and we're interested in the electric field, a distance z, which is 10 centimeters away from it. We're also told that the charge on the ring will be plus 4 microcoulombs. Now part A, what is the linear charge density? That'll be the total charge divided by the length of that line of charge, and the length will be the circumference of that circle. So we have Q over 2 pi r. That comes to be about 0.126 meters in length, and so we have lambda will be 4 by 10 to the minus 6 over our 0.126, and we get about 3.18 by 10 to the minus 5 coulombs per meter. Now the next part, electric field, 1 over 4 pi E naught, QZ over Z squared plus R squared to the 3 over 2. And that will be 8.99 by 10 to the 9. Q is 4 by 10 to the minus 6. Z is 0.1. And we have here 0.1 squared plus 0.02 squared to the 3 over 2. And that comes out to be about 3.39 by 10 to the 6 newtons per coulomb, and the direction is away from the ring, or in the plus Z direction. Now part C, what would the electric field be right in the centre of the circle? Now think about the net force. A positive test charge right in the centre would be equally repelled from every point on the ring, and so there'd be no net force, and so there'll be no electric field. Now if Z were very large, let's just look at the equation. 1 over 4 pi E naught QZ over Z squared plus R squared to the 3 over 2. Now if Z is very large, then Z squared plus R squared, well basically the R squared becomes insignificant. So that simply becomes equal to Z squared. Then we would have Z up the top. Down the bottom we have Z squared to the 3 over 2, which is Z cubed. So that gives us our electric field is a few constant terms times 1 over Z squared. So that will be tending to 0.